This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. This video is about clause 11, detailing of reinforcement, part 2. To calculate the needed mandrel diameter, we can rearrange the formula 11.1 as we have seen in the previous video. Because this formula 11.1 is not that easy to in use. So we've seen that if you use in this formula as the mandrel diameter equal to the minimum mandrel diameter, that you run into trouble because sigma SD is smaller than the design value of the steel of the yield strength. So that creates a problem. So now we know that in most cases you will use a mandrel diameter which is larger than the minimum value. So now let's look at this formula 11.1 and we rearrange it so that we take the ratio of the mandrel diameter divided by the diameter of the rebar, and then you will see this must be bigger than what is stated in this formula. Let's just take one particular case. We take concrete quality of 30 megapascal, the design value of the yield strength 435 megapascal, the angle of the bend 90 degrees, for instance, for stirrups, and the maximum size of the aggregate 32 millimeters. And CD, we will take again the minimum of 40 and 3.75 times the diameter. The 40 is just something that I've chosen. It's the concrete cover plus the stirrup diameter. We look again at the graph. X-axis is the diameter of the rebar, and this time on the y-axis it's the ratio of the mandrel diameter divided by the diameter of the rebar. The black line is the line for the minimum mandrel diameter. So you will see that for diameter smaller than 16, it's 4 times the diameter, and for diameters bigger than 16, it is 7 times the diameter. So in fact, when you look at this curve, it should stop here and then go horizontal, because you cannot go below the minimum required mandrel diameter. But for just to visualize it, I've drawn this whole graph like this, and that's what it means not okay. It means it should be horizontal here. And this is okay, it means that the value is okay. So at the 90-degree bend and FYD equals 435 megapascal, full capacity of the stirrup, for a diameter bigger, diameter of stirrup bigger than 12 millimeters, then you need a mandrel diameter which is larger than the minimum required diameter. You see it very clear on this graph. You always end up with it. For instance, if you use a stirrup of diameter 20, you will end up with 12 mandrel diameter of 12 times the bar diameter. You can also put all those numbers into a table. Of course, negative values is not possible, but just to make it complete. You see now for concrete grade 3037, this was the graph on the previous slide. Now we have done it for all concrete grades, and you will see that the red zone is at 90-degree bend for stirrups. The mandrel diameter must be bigger than the minimum. So this is the red zone. In fact, I should have written here up till 16 millimeters. I should have written here everything bigger than 16. I should have written 4. And larger than 16, I should have written here, those numbers should be 7. But just to show, this red zone shows you where the minimum diameter should be used. In all other cases, you see very clearly that the mandrel diameter, the minimum mandrel diameter, is not okay at full capacity of the stirrup. And you can see that the numbers are sometimes very high. If you take C2025 and you use a stirrup diameter of 20, you need a mandrel diameter which is almost 20 also, and 20 times the diameter, which is 400. So this is quite large. So take care of that when using stirrups, that the mandrel diameter is okay. We can now, from the previous graph, from the previous table, we can make a graph. X-axis, it's the diameter, and the y-axis, it's the ratio of the mandrel diameter divided by the diameter. And again, we have here the minimum value of the mandrel, and the concrete quality increases from top to bottom. Here you have 4 times the diameter up to diameter 16, and here you have 7 times the diameter as from 16 onwards. In most cases, you will see that the minimum mandrel diameter is not applicable, or you can also see that when the concrete quality increases, high strength concrete, all those curves are coming almost one on top of the other. You will see that for high strength concrete, the minimum mandrel diameter is ruling, is governing. We also notice that the low grade concrete needs much bigger mandrel diameters, even up to 40 times the diameter. We can now take an example for a pin where alpha, when the angle of bend is 180 degrees, with the same conditions as in previous example. We look at the graph again, and then this time you will see that all mandrel diameters must be bigger than the minimum mandrel diameter at full yielding of the pin. And this for all diameters used. Again, we can put it into a table where the red zone is where the mandrel diameter must be bigger than the minimum, of course. Here it should be stated above 16. Here in this, it should be stated 4, and this would be 7 instead of 6.8. In all the other zone of the table, there you will see that you need a bigger mandrel diameter than the minimum one. Again, we can now put it into a graph, all cases for a pin, and the minimum mandrel diameters are not applicable in most cases at yielding. You can see it clearly. This is only for high strength concrete, but it's a small zone. So you can remember that when you're using a pin, you cannot use the minimum mandrel diameter at yielding of the pin. Now there are some simplified detailing rules in 11.33, and I have taken a copy directly from the code, version 2023, because this text is rather confusing. It states that provided that provided that this condition is prevailing, then the verification of the concrete inside the bend of the mandrel may be omitted. For what? It may be omitted for stirrups and links, and it may be omitted for standard hooks and bend anchorage complying with the figure, and then all this must be true. It's impossible that all conditions must be fulfilled at the same time, because we've seen that stirrups and links do not comply with Formula 11.1. We've seen that in the previous videos and slides. On the contrary, when there is a standard hook and bend anchorage, then all those conditions here, the four conditions, must be complied, because the word "and" is at the end here of this sentence. So this is not clear. For instance, this condition FYD smaller than 25 FCD, is that also valid for this or not? So it's not very clear. So like I said previously, we have seen that the rules in 11.3.3, they do not comply with equation 11.1 for stirrups and links. Unless we use a factor called K trans, then the stirrups and links do comply. And this factor K trans is defined in 11.3.5. If transfer bars are placed within the bend, the limit to the steel stress sigma SD in Formula 11.1 may be increased by the following factor, which is K trans. Just some definitions. When you have bend in a rebar, for instance, for 90 degrees, and you have one rebar in the corner, not the mandrel diameter, but the rebar in the corner, then this rebar has a diameter of phi trans, from transfer bar. Of course, this is not according to scale. Normally, phi trans is a little bit bigger than the diameter of the stirrup, for instance. This factor, K trans of K transverse, is equal to the formula 11.2. And N trans is the number of transfer bars within the bend. Now, in most cases, this is only one. In fact, it's in a stirrup, for instance, you need in each corner at least one bar. So N trans is always there, or in most cases for stirrups, it is there. And phi trans is, of course, like we said, the diameter of the transverse reinforcement. And this diameter must be smaller than 1.35 times the diameter of the stirrup, of the bar with the bend. Now we'll look in what this formula does. What are the practical values of this formula of K transverse? We take a normal case of one bar in the bend, and we take the case where the diameter is equal to where the diameter of the stirrup is equal to the diameter of the transfer reinforcement. In all cases, phi trans is bigger, but if phi trans is bigger than phi, then this factor K transverse gets bigger. So by doing this, making this at least the same diameter, I'm on the conservative side. And we assume that the mandrel diameter is equal to the minimum mandrel diameter. Okay. And now we can see what will happen to the factor K trans. We have, in fact, 4 cases, 2 for an angle for an angle of 90 degrees and 2 for 180 degrees. And in the 2 cases for 90 degrees, we have a diameter of stirrup smaller than 16 and bigger than 16. The same for the pin, smaller than 16 and bigger than 16. And then we know that the minimum mandrel diameter equals to the mandrel diameter. So that means 4 feet, 7 feet, 4 feet, and 7 feet. And then you can easily calculate the factor K transverse, and you see it will come to 1.5, 1.29, 1.25, and 1.14. So what will be the effect on the sigma SD, like we've calculated in the previous slides and videos? I've taken the summary table again for the different concrete grades in function of the diameters of the rebars. And then you will see the red zone is the maximum allowable tensile stress is smaller than 435 megapascal. So that's what I've indicated as red. You see now that the situation is a little bit more, it's better because for C30, you can now use stirrups, for instance, because this is 90 degrees, up till not 20. You cannot use it to the full capacity, but up to 16. So that's better. But remind yourself that using stirrups with a transfer bar, you still have to check the maximum steel stress in the stirrup for large diameters of stirrups. For an 180-degree bend, we have done the same calculations. We corrected the same values. And you see here also that in the red zone, the maximum allowable tensile stress is smaller than 435 megapascal. And you you see that, for instance, for C30, you can never use the pin to its full capacity, even with the correction factor of K transverse.